Hello everyone and welcome. Today we are going to examine a fundamental challenge in modern infrastructure and explore how advanced materials science proposes to solve it at the nanoscale. We live in a world built on concrete. It is the bedrock of our cities, our bridges, and our highways. However, this reliance comes at a steep environmental cost. The building industry consumes vast amounts of energy and generates considerable CO2 emissions annually. According to reports, more than 30% of the annual global primary energy demand is tied to buildings, which results in a massive energy expenditure. Because the production of cement, the essential binder in concrete, is so carbon-intensive, the scientific community faces a clear directive. We must find sustainable alternatives and drastically reduce our carbon footprint. The most logical pathway to achieving this is to make concrete fundamentally stronger and more durable. If we can significantly increase the structural integrity of the material, we can use far less of it to build the exact same structures. Less concrete means less cement, which translates to an immediate reduction in global CO2 emissions. For years, researchers looked toward carbon nanomaterials to achieve this, with traditional graphene being the primary candidate. Graphene is a two-dimensional carbon lattice known for its robust mechanical stability. However, attempts to integrate flat, two-dimensional graphene sheets into cement mixtures encountered a severe technical barrier. The dispersion of regular graphene in cement mortar is highly problematic. Due to the highly alkaline environment of the cement matrix, flat graphene sheets tend to agglomerate. Essentially, they clump together, completely losing their unique properties and failing to reinforce the material. The solution to this problem was found by changing the geometry of the carbon structure itself. Enter a zero-dimensional nanostructure known as Carbon Nano-Onions, or CNOs. From a morphological perspective, Carbon Nano-Onions consist of quasi-spherical and polyhedral-shaped graphitic layers situated close to one another. You can visualize them as multi-layered fullerenes, where concentric graphene shells are nested inside each other, much like the layers of an onion. The distance between these graphitic layers is 0.3, which is virtually identical to the distance between two graphitic planes in ideal graphite. Why does this spherical shape matter? It completely solves the dispersion problem. The spherical nature of the material leads to a unique ability to be dispersed uniformly in a variety of media. Unlike flat graphene, carbon nano-onions do not stick together. They can be easily and homogeneously incorporated into the matrix. But what exactly happens on a chemical level when these carbon spheres are introduced into a wet cement mix? Normally, when cement mixes with water, it forms a cement glue made of calcium and silicate crystals that holds the structure together. When we introduce carbon nano-onions, these tiny spheres act like microscopic magnets. Their surfaces have special oxygen groups that actively pull in calcium ions. This forces the cement glue to grow rapidly and densely right around each individual sphere, instead of forming randomly. As a result, the internal structure of the cement becomes significantly denser and more organized on a micro level. This localized organization translates into remarkable macroscopic properties for the concrete. Mechanical reinforcement. Concrete is inherently prone to micro-cracking under stress. The spherical morphology of carbon nano-onions enhances uniform stress transfer and suppresses crack propagation through mechanisms known as crack bridging and deflection. When a microcrack begins to form, it encounters these dense carbon spheres, which absorb the energy and deflect the crack, preventing it from spreading. As a result, the addition of graphene structures can increase the compressive strength of concrete by up to 146% and its bending strength by up to 79.5%. Barrier properties and permeability. To truly appreciate this, we need to look at what happens when concrete cures. When ordinary concrete dries and the water inside it evaporates, it leaves behind a network of microscopic empty spaces or pores. You can think of standard concrete almost like a very dense sponge. Over time, water, road salts, and aggressive chemicals seep into these pores, which eventually rusts the internal steel reinforcement and destroys the structure from the inside out. Carbon nano-onions completely alter this porous structure by changing the chemistry of how the concrete cures. When added to the mix, these carbon spheres promote the uniform hydration of the cement. They act as highly active seeding or nucleation sites because the oxygen functional groups on their surfaces physically attract calcium ions. As a result, the essential cement crystals, which act as the glue of the concrete, grow directly on these spheres in a much more organized structure. This accelerated, organized growth creates a surge in the quantity of solid hydration products inside the material. This extra solid material physically fills up and shrinks the larger harmful voids, known as mesopores, resulting in a significantly denser and stronger cement matrix. By effectively clogging these microscopic pores, carbon nano-onions reduce the concrete's permeability by a staggering 400%. The material improves its structural cohesion and becomes incredibly resistant to moisture and aggressive environments. In the real world, for structures like marine piers or highway bridges, this means destructive salt water simply cannot penetrate the material. This stops internal corrosion in its tracks, allowing these massive structures to stand for 50 or more years without requiring major repairs. Thermal stability. Temperature fluctuations cause internal stresses that gradually degrade infrastructure. The integration of graphene increases the thermal conductivity and heat capacity of concrete by 88%. This crucial enhancement improves heat dissipation and reduces local thermal stresses within the concrete matrix. By mitigating these thermal stresses, the material becomes far less susceptible to temperature-induced embrittlement. In conclusion, transitioning from two-dimensional graphene to zero-dimensional carbon nano-onions is a prime example of how nanoscale engineering can solve macroscale problems. By utilizing a spherical geometry, we overcome the chemical hurdles of dispersion and actively manipulate the crystalline growth of cement. By engineering concrete that boasts such extreme increases in strength, durability, and impermeability, we unlock the ability to design lighter, more efficient structures. Utilizing less material without compromising safety is a scientifically sound, immediately actionable strategy to drastically reduce the carbon footprint of the global construction industry. Thank you for your time. I look forward to your thoughts and questions on the future of nanocomposites and civil engineering.